Hi, I'm Lindy Bingel, and this summer I entered with Gala Wind to look at the Canadian wildfires and cloud formation here in the United States. As I'm sure we all know, this summer there have been wildfires in Canada, which have caused large amounts of smoke to be present all across the eastern United States. I know that in my hometown in New Jersey, we had AQI scores upwards of 300. Essentially, we wondered if the smoke had any effect on cloud formation. As I mentioned, we wanted to see if the smoke from the recent Canadian wildfires has affected cloud formation. We aimed to look at the differences between clouds this year, in 2023, and last year, in 2022. This was more of an open-ended project, as we essentially just gathered and compared information. Although we did not make any formal hypotheses, I would have guessed that there would be fewer clouds this year. At first, I had to learn to use a Linux operating system and code in Fortran, which, as my mentor keeps telling me, is still in use. On the screen now, you can see some of the code that I wrote while I was playing around and learning. However, I had to wait for this laptop to be shipped to me, which was a project in and of itself with shipping delays and such. I could, for the summer, honestly say that I had a NAS computer. In the meantime, I looked at USitis Worldview. There, I could see clouds on specific days, along with what day of the year it was. I could also estimate the time that the data was taken in different areas. This information would then be used to download specific satellite data. You see, downloading unneeded files would be unnecessary while taking time and space. So this way, we could narrow down the pool to what we actually needed and found important. We were only interested in seeing fair weather cumulus, which are the little spotty clouds. Then, we could use Panoply to see the satellite data visually and locally. However, this was only temporary because soon I needed to learn some Python. My mentor gave me a stub and told me to write my own code to visualize the data. I had many unsuccessful trials. However, in the end, I had my own working code. So first, we had to cd into the correct folder, which basically means that we're moving into the correct directory. So first we had to go into downloads, and then into folder, which is the folder I had in downloads. I named it folder because I thought it would be easy to remember. Then you have to put in the actual input for my code. So first you have to put Python 3 to tell the computer that that's what you're going to be using. And then you put in the name of the Python, like the code, which you can see here is finalcode.py. And you can also see it in the folder. Then we're going to put the full name of the Modo6 file. In this case, I just named it Modo6, which is one of the files that we downloaded. However, I just renamed it for ease. Then you put the name of the variable that we're going to be looking at, in this case, cloud optical thickness. And then we are going to input the name of our output file, what we want the image to be saved as in our computer. You could put a full path here if you wanted to save to a folder that is not the downloads folder, like the folder in downloads, but that's fine for now. And then we're going to put in the title of the image that will appear like in the actual image. You can see here. And then you need to put in the color map that you're going to use. In this case, I've been using Veritas. And then a few things pop out because that's just like a fun way, an easy way to check if your code is working is to just put prints in sometimes to see where an error actually is. So that's not actually relevant to the code itself and its output. And then here you can see that the image is actually saving. So you can see it saving there. And then you can see it pops up on the screen. Right here, it takes a second to load. I do have it say close in order to like get the prompt back because you need to close it in order to get the prompt back in the console. So yeah, that's my code. However, this was not the end, as we still needed to manipulate the data further. There were even more files to download. Then we could put these files into a program which would output a text file with two columns. The first column is the day of the year, and the second is the mean aerosol optical depth. This information could be used to make this graph. That is, after I wrote more code, which also had many iterations. And that's where I'm at right now, so I'll be back in a few days with updates. Alright, I'm back. Here, you can see a recording of me figuring out the last bit of data analysis. It's basically the same as making that plot from before, except looking at different information. Now for the best part of the project, results. So here are the two main charts that show the differences in clouds between 2022 and 2023. As you can see, 2023 has a higher aerosol optical depth on average than 2022. The cloud fractions for both years varied, but both years had a low of 0%, and 2023 had a higher maximum of 100%. 2022 only had a maximum of 70%. So first, the aerosol optical depth essentially just shows the amount of smoke in our study area. Technically, it tracks 15 different types of aerosol, but in 2023, smoke was most prevalent. Thus, the higher aerosol optical depth in 2023 shows how there was much more smoke in the atmosphere this year than last year. Now, onto the cloud fraction for both years. But what exactly is a cloud fraction? Well, it is a measure of the number of cloud pixels that are liquid water over the total number of pixels in the area. Essentially, though, higher cloud fraction just means more clouds. You can see in the graph that there is not a noticeable disparity between cloud fractions in 2022 and 2023. Therefore, our results are inconclusive as to if the smoke from the Canadian wildfires affected cloud formation. Okay, so the results are inconclusive, but why? Well, first off, the smoke might have been high enough in the atmosphere by the time it reached our study area that it didn't interact with the clouds. Then, the smoke would have had no effect, given that there would have been no interaction to study. Second, we may have gotten clearer results with a different methodology, which I will touch on more later. Third, we may have just not studied enough data. But lastly, there might just be no effect. However, we would need to do much more in order to prove the absence of an effect beyond a reasonable doubt. Unfortunately, this marks the end of the project for me as I have other obligations during the school year. However, the question of if aerosol affects clouds is still very much an open research topic. Studies can be done on the topic with more data. For instance, this could be studied globally instead of just in the Midwest. Also, more years could be considered. More satellites and instruments could also be utilized to find out more. LiDAR could be used to see if the smokes and clouds really were close enough to interact. The effects of aerosols such as smoke on rain could also be studied. All of this could take years. If I were to redo this project, I can't think of anything I would have done differently per se. However, we did hit roadblocks which we needed to work around. As I mentioned, there were shipping delays and problems getting the laptop to me. That delayed progress. Also, at one point I sent code to my mentor, but the email got blocked because it had that attachment. We didn't realize that I had sent an email without it going through for a few days, and then we needed to work around it by uploading our code to a shared Google Drive folder instead. Now, I just want to thank everyone that made this project possible. I am so glad that I had the opportunity to work with my mentor, Gala Wind. It is so crazy to see how much somebody can know about something that you've never even thought of. Now, I think I'm taking questions.